to the presentation with Paul and John. So our speakers today, Paul Blackwell, who is the Director of Knowledge Exchange within the University of Strathclyde for the Department of Design, Manufacturing and Engineering Management, and John Storr, who is a Senior Manufacturing Engineer within the Advanced Forming Research Centre's forming team. Housekeeping for today. The webinar will be recorded, so you will be presented with an option of watching it again if you enjoy it that much. Available on our YouTube channel. Your microphones and your webcams will be turned off. If you do find yourself, if they do pop back on, if you just please prevent feedback, just pop them back off again, please. The chat tool will be available for the full hour, so please, if you have any questions throughout the day, if you just type them into the chat tool and we will answer the question and answer segment at the end of the presentation. If you're looking to prompt or the NMIS online, if you could use the hashtag NMIS Insights for any questions on Twitter, they'll get through to us that way, and indeed on LinkedIn as well. And there will be a short survey sent after the webinar, just asking for some feedback on your experience and how you enjoyed the day. So, for those of you who don't know, the National Manufacturing Institute Scotland is the newest venture, and it is an industry-led manufacturing research and development facility. It will be an open access centre where the public sector and industry will be brought together, and as it says there, to transform skills, productivity and innovation. And hopefully the aim is to make Scotland a global leader in advanced manufacturing by pulling together all the resource that we have available in Scotland. In terms of what NMIS actually will do, it's looking to reduce the barriers to innovation. We all know the problems that some companies may have in terms of access to information or technology. Hopefully NMIS will combat that. We're looking to stimulate investment and increase manufacturing competitiveness for Scottish companies and be a catalyst for job creation and strengthen the supply chain links over across multiple sectors throughout Scotland. We hope to inspire and attract some new talent, new technology, and looking at current equipment and how we can actually transform that the business needs. We'll also be working with all businesses of all types and sizes across multiple sectors, as already said, and hopefully providing full benefits across Scotland. NMIS is part of the One Scotland team, and I won't read out every single one there, as you can see it there, but we are operated by the University of Strathclyde, and we are supported by and collaborate with multiple different partners who have got the same aim, benefits. In terms of the NMIS group, today you will be hearing from one of the specialist technology centres, which is the Advanced Forming Research Centre, which is specialising in metal forming and forging and materials. There will also be other core elements of the NMIS once the building is operational, 2021/2022, and that will be a digital factory, collaboration hub, and of course the Manufacturing Skills Academy. Of the specialist centres, 2 are already open, the aforementioned AFRC, and also the Lightweight Manufacturing Centre, specialising in lightweight materials and composites. In terms of the research programme, the core research programme for the AFRC, these are just examples of the types of things that we will look at. Today we're going to be concentrating on hot sheet forming. So without further ado, we'll watch a little snappy video, and then we will get straight in to the next speaker. It'll be Paul Blackwell. Thank you. Paul.
Okay, thanks, Stephanie, and welcome everybody to our webinar on forming and indeed superplasticity. We thought we should start off actually by a bit of an introductory slide just about superplasticity itself. So in terms of definitions, what is superplasticity? Well, it's an enhanced form of plasticity as the name suggests, that we can obtain in certain materials deformed under some fairly closely controlled conditions. So to put that into context for you, if you think of a reasonably ductile material like mild steel, if you would take a rod of mild steel, put it into a tensile testing machine to see how far you could pull it before it broke, you would typically get somewhere between 20 to 30% extension. So that would be, you know, quite a high level of ductility. In the case of a superplastic material, as you can see from some of the examples there on the bottom right of the slide, we're actually an order of magnitude up on that, and we can get many hundreds of percent extension. And indeed, there may still be a world record for a bronze where, in fact, they managed to get several thousands of percent extension. Now, of course, these very high elongations are not of too much relevance in an engineering setting, and in fact, in most superplastic forming operations, you know, the maximum elongation that we would see in a part would be 100% or less. Because clearly, if you start off with a sheet of material that's a couple of millimeters thick, by the time you've stretched it for about 100% of extension, then the residual thickness of the material is starting to get so thin that it's of no real engineering use. Now, to jump back to my definition, I said that superplasticity is not a property that all materials demonstrate, and you see a list on the bottom left there of some of the alloys that are commonly superplastically formed. And really the main ones are the aluminium alloys, and you see a couple listed there. 5083 classically is a very classical superplastic material. And in the case of titanium, which is the other main material that tends to be formed by a superplastic forming process, Ti64 is the most widely used alloy. What these materials will all have in common is that they have a very fine grain size. So they're being carefully processed through the various sections of the rolling mills to generate a grain size of 10 microns or less. That's the sort of target that we aim for. And basically, in that context, the finer the grain size, the better. And the reason that that's important is because the grain boundaries play a big part in the actual mechanism of superplastic deformation. I won't go into that anymore, but if anybody wants to talk a bit about more about that, we can pick that up at the end. So superplasticity, enhanced plasticity, we can get it in a reasonable range of materials, but we do need some fairly carefully controlled conditions in order to be able to generate it. Some detail around that. For aluminium alloys, we will be forming them at around 500 or perhaps slightly more. See? For the titanium alloys, or Ti64 is the main one, that forms at around 900 degrees C. And the little clip that you just saw there was of a big SPF press, and that was, as you saw, sort of orangey red. So that would have been around 900 degrees C. If we can move to the next slide, Steph. So the process itself, what does it involve? Well, this is a nice little set of schematics which kind of walks you through it. To carry out a superplastic forming operation, you obviously need to source your sheet in the first place, cut it to the appropriate size for the preform, and then what's done is the sheet is put into a press of a suitable type that has heating capability, and then clamped between the tools. And it's clamped so that it's gas tight, and then we actually form the sheet using gas pressure, and in this country we'd be using argon, to actually blow the sheet into the shape of the tool, as you see demonstrated there. Now, if you've never come across superplastic forming before, this all sounds a bit unlikely. You can take a sheet of metal and blow it into a shape just using gas pressure, but it is possible, and it's something that we do a lot, and that is the nature of the superplastic forming operation. Now, what we've shown you here is just a single sheet forming operation, and if we just jump to the next slide, there are variants of this. We can either use single sheets, or we can, under some circumstances, and this is done with titanium alloys, create parts using multiple sheets. And there we take advantage of a process called diffusion bonding. So what we're showing in that bottom schematic there is a 3-sheet part. So let's say the 3 sheets of titanium 64, they will have gone through a careful cleaning process to make sure that the surfaces are nice and clean. And then what we would be doing there is applying a bonding inhibitor, or more generally known as a stop-off material, that inhibits bonding in certain areas. And that's important because we want those areas later, they become basically the gas paths for when we then subsequently inflate the part to form the sort of shape that you see on the right. So what we do is clean the sheets, apply the bonding inhibitor. We then take that pack, heat it up to a fairly high temperature under mechanical pressure, and we have this process called diffusion bonding. Titanium is unusual as a metal in as much as it dissolves its oxide film. By holding the pack at a high temperature under pressure, the material bond lines completely disappear. And if you do the process properly, you effectively end up with a monolithic piece of material. We can then, as I say, take that and then put it into usually a different piece of equipment, an SPF press, and then by pushing gas pressure into it, actually inflate it to give the sort of shape that you see there on the bottom right. That's called a Warren girder structure. And where has this sort of process been used? Well, very famously by our good colleagues at Rolls-Royce to make a wide chord fan blade, and they've been doing that for many years now, many decades in actual fact. And why would you bother? Well, it gives you a very nice combination of lightweight with good stiffness and strength in the part. Okay, so that's a little bit about the superplastic forming operation from sort of practical point of view. If we just move to the next slide. So this slide just attempts to sum up some of the advantages of the process. So why do we do it? Well, there are some alloys that just can't be formed cold, and titanium 64 would be a classical example of that. Its formability in a sort of classical cold pressing operation is very limited indeed. So using the superplastic forming process opens up a whole range of possibilities for alloys like that. But the other main advantage of the process is because the material is superplastic, it allows us to form complex near-net geometries. And the reason that they are near-net is because we don't have any problems with springback. Now, just in case you don't know what springback is, if you cold press a sheet, you bring the tools together, squeeze the metal into the shape, and then as you pull the tool in apart, the metal will spring due to its elasticity. And that can be a problem, particularly with more complex parts. And it takes a little bit of designing against. It's not the easiest thing to do. In the case of superplastic forming, we don't get any springback. Why? Because essentially we're annealing the piece as we're forming it due to the relatively low forming speeds. And the second main advantage is because of this capability to form complex geometries, it can allow, under some circumstances, what may otherwise be quite complex fabricated assemblies with many separate parts to be redesigned to be formed as one part. And there are many good examples, particularly from Boeing, where they've actually done that retrospectively, looked at part assemblies and said, well, actually, we can form this just in one SPF part and greatly reduce the part count. And of course, when each one of those parts has needed its own tool set to make that part, then the overall cost reduction can be very substantial. If we move to the next slide, Steph. Of course, it has its challenges, and any manufacturing process that you care to think of will always have its challenges. And the principal one is that it has reasonably long cycle times, certainly compared to many cold forming processes. For a single sheet part, typical forming times are perhaps around 30 minutes per part. But for the more complex multi-sheet parts, it can be several hours to actually manufacture a part. So superplastic forming is something of a niche thing. It's tends to be used in sort of high value add type applications, and we'll come to a few of those subsequently. Just staying on this slide for a second, in the case of titanium specifically, because we're forming at very high temperatures, the tooling needs to be stable at those high temperatures, and therefore the sort of tools that we use are very highly alloyed, so they're quite expensive. The titanium itself can be subject to oxidation. It forms something called alpha case, which needs to be then either milled or chemically pickled off. So that adds an extra stage to the process. And because superplasticity, the sort of optimum superplastic properties are only obtained within a fairly tight range of temperatures, we need to have reasonably good temperature control of our apparatus, and we normally would aim for plus or minus 10 degrees C. And in the little video that Stephanie was showing you earlier on, the thing that we're actually taking out of the press there was, in fact, what's called a search blade. So that's a blade that had been put into the tools to actually measure the temperature across the whole tool setup to ensure that we were hitting our temperature control limits. The other thing is, if you're actually making a new part using superplastic forming, you will need to do a bit of work to optimize your pressure time control curve. That's the rate at which you put the gas into the part in order to reduce the forming process as much as possible in terms of the time. But that's fairly easily done these days by finite element modeling. If we can jump to the next slide, Steph. So one of the things we said we'd talk about was what's going on in the world of superplastic forming, what are the recent trends. And the top two really relate to titanium alloys that are probably the most difficult materials to form using superplastic forming in some senses. There's a big push over the last few years to look at the use of ultra fine grain materials. So these are classically Ti-64 that's been processed using very careful rolling procedures to actually generate a grain size of less than 1 micron, so very fine indeed. And why would you bother doing that? Well, it gives you an opportunity, if you're interested in SPF of titanium, of either reducing the forming temperature or increasing the forming rate. These are both good things, of course, but most manufacturers would tend to want to reduce the forming temperature, because by reducing the forming temperature even by 50 degrees C, or better 100 degrees C, which is what these ultrafine grain materials do for you, you can greatly improve your tool life. So if you're on a big production run, you don't need to take the tools out, clean them up, and then put them all back in again on such a regular basis. So that's a big bonus. The other thing that people have been looking at over the last few years, and some of our colleagues at TIMET have spent a lot of time working in this area, is modifying the chemistry of titanium to actually reduce the SPF temperatures. We can now form a range of titanium alloys in the temperature range that you see there, 800 to 850 degrees C. Nice example of that would be Ti-54M. Final point on that slide. This is still really at a research stage. I'm not aware of anybody using this industrially, but people are investigating the use of hot drawing combined with superplastic forming, as you see demonstrated in the schematic at the bottom. And what's going on here is that we're using a deep drawing process to put in most of the deformation fairly quickly, and then we just take advantage of the superplastic properties of the material to actually do the final part of the forming operation, where we really want to get that detail and generate the sort of complex geometries. The combination of the two produce some fairly marked reductions in cycle time for the process. If we jump to the next slide, Steph. Some applications. Now, apologies on this slide, because we would have liked to have shown you lots of nice pictures of all of these parts. Unfortunately, copyright rules don't allow us to pull pictures off websites and just put them where we wish. But I would draw your attention to the references at the bottom that will show you some very nice pictures of all these parts. Aerospace. So engines, I've already mentioned fan blades, and fan blades, that for those of you who don't know, are the big blades right at the very front of the engine. They've long been made, as I say, by companies like Rolls-Royce, by a superplastic forming, an SPF DB process, because those are fusion bonded as well. Guide vanes and various tanks are all made by superplastic forming. And indeed, tanks for satellite launch vehicles have also been made by SPF in the past. On the actual aircraft itself, you see a range of examples there. SPF often used to make door panels of one type or another, simply because it gives you an opportunity to form what is otherwise a difficult to form material with the sort of detail required. A nice example at the bottom, slightly old one, I will concede, back to 1991, but it does just give you a bit of an example of what can be done when you use the process properly. 8090 is an aluminium lithium alloy used to make a military aircraft door with a very significant weight saving, and as you see, a 68% cost reduction. So if you design for use with this process, you can really take advantage of it, and it needs to be done that way in order to get those sort of cost savings. If we just move to the next slide, some applications in automotive, mainly aluminium for automotive, of course, and you see reference to companies like Superform and Alcoa there. The sort of cars that this is used on, Bentley Continental GT, Mercedes AMG SLS, these are obviously top-end cars. And what you see is that a lot of the sort of external panels are made in aluminium using the SPF process. Again, an example at the bottom there, just of a prototype where, using suitable design, you can end up with using one part instead of three, which will be necessary using a conventional forming technique. And there are secondary advantages there if you can design for SPF, reduce your part count, because normally, obviously, if you're using a fabricated assembly, it will be riveted together, it will be welded together, and rivets and weld lines are areas where failures can occur, which are completely alleviated if you use a single part. Jump to the next slide, Steph. So this is the final one from me, and it tells a little bit about the story of the AFRC in specific, in terms of what we've done and where we are with the process. So we moved into our present building back in 2010. We're situated right next to Glasgow Airport, for those who aren't familiar with us. We very rapidly established an extensive set of mechanical testing equipment, so we can characterize the materials that we're talking about here very fully. We also back that up with a very full set of metallography capability as well. And obviously this is common to many universities, but what you wouldn't find in many universities is what we then acquired in 2013 and 2014. Initially a 200-ton press from ACB, French company based in Nantes. And then the year after, what the press that you saw briefly in the video earlier on, a 1,200-ton Superplastic Forming press with a pattern size of 2.4 by 2 meters. As far as I know, that is the biggest SPF press of any research establishment in the world. There may be one close to it in China. And in fact, is one of the biggest SPF presses in the UK, either inside or outside of a university. I'm aware that BAE Systems have got a slightly larger SPF press, but it certainly is a very substantial size press. So the point about this is we can do sort of full scale forming operations. Final point, 2020, we had a bit of a think about the number of projects we've done over the years. We've worked with a whole range of customers on Superplasticity, both looking at it from a fundamental point of view and from a very much more practical point of view. And we reckon over the years, we've done about £10 million worth of work across a whole range of projects. And I'm now going to hand you over to my colleague, John Storr, who's going to walk you through a little bit more on that.
Okay, thank you very much, Paul, and thanks for all your insights into the SPF process there. So where Paul has spoken a lot about the principles of the process, what the capabilities are, the advantages and challenges of SPF as a whole, I'm going to talk a little bit more about superplastic forming at the Advanced Forming Research Centre, what capabilities we have, how we benefit our customers, and then some of the kind of publications and work that we've done in the past as well. So Paul spoke a lot, as I said, about the kind of introduction of SPF, and he just left us there with a slide on how the AFRC's story has been so far. So I'm going to just briefly go through some of our capabilities in-house. And as Paul mentioned, one of the benefits that we really have in SPF is the full-scale manufacturing equipment that you maybe wouldn't typically find in a university environment or a research centre in particular. The first piece of SPF full-scale equipment we received in the centre was our 200-ton superplastic forming press. As Paul mentioned, this is an ACB press. and this was installed in 2011. It has a platen size around 720 by 720 millimeters, and it's used typically to prove out process cycles, to look at new material implementation, and to look at different perhaps material structures and different geometries that we want to investigate with different pressure cycles before we perhaps move on to then apply those to the larger press that we have. So Steph, if you want to go to the next slide. We have then our 1,200 ton superplastic forming press, and this also has a quite unique capability of creep forming. So along with the 1,200 ton SPF capability, it also has 600 ton of creep forming capability. So not only using the gas pressure to form components, but we can also just use the tonnage within the press to creep form thicker sheet components. And we've done that with some thicker sheet titanium components in the past as well. As shown, compared to the 200 ton press where we had a platen size of around 720 millimeters, we've got quite a significantly larger heated platen area in this press of 2.4 by 2 meters. And that allows us then to work directly with our customers on full-scale manufacturing components, which allows them to carry out research on our presses without having to take their presses offline, which is a huge benefit for them. They don't lose production time, and then we can apply directly to prove out the process that we are wanting to investigate on that full-scale equipment, which is really essential for what we want to prove. Let's move to the next slide, please. So, as well as the larger scale pieces of equipment, we have a number of complementary pieces of equipment that I'll talk about just now. We have our automated die part interface testing machine. This is a unique machine that we had purposefully made for the AFRC. And what we're trying to do here is replicate die wear activities on a very small scale using small coupon samples. Automated so that multiple parts can be run to simulate a process such as would be done in a manufacturing setting. And then it will allow us to assess things like die wear, tool material, and assess also lubricants and coatings, so that then we can understand if perhaps a novel lubricant, a novel coating, or a novel die material would be suitable for the process. And the principle of this is that we have the die stack, we have a furnace that will clamp over the die stack with a component, and you can just see the small coupon component sent at the bottom of the image. The top die stack will rotate while applying a tonnage, and that will then simulate the SPF process. It doesn't have a gas pressure involved, but it's purely to simulate the die interaction with the component there. And then we can use that, as I say, to analyze these different coatings before then applying that to larger scale components, where we obviously would cost more to do, and you risk the run of having things not work out on large scale parts first. You want to always test these on that smaller scale. That's one of our complementary processes. And Steph, if you go to the next slide. Another really key complementary process we have is our mechanical testing, and Paul touched on this briefly before as well. One of the aspects of this is our Zwick Z150 machine, which is a similar setup to what I've just described in the die part interface rig that we have. You have a furnace wrapped around a die stack. The die stack is used specifically to hold a tensile component. You're heated perhaps in either argon or air, depending on the type of test they're going to, with capabilities up to 1,200 degrees. And then the test component, the tensile test, is elongated by the machine at a specific set strain rate, and that allows us then to gather really, really crucial data about that material. And you can see an example of a strain rate jump test in the graph there. And that lets us essentially then feed into some of the process modelling activity that we run for superplastic forming, which I'll talk a little bit about further on in the presentation. If you go to the next slide. So a slide here which is going to talk through for a bit of time on the AFRC's capabilities and our specific expertise. So what we offer in the area of superplastic forming and some examples of work activity that we've done in the past. And I think the key thing that I want to really highlight here is that we don't just focus on the SPF process. And from what I've already said, you'll see we have some complementary processes. But rather than just focusing on SPF itself, we focus on the entire process chain involved with SPF. So that's pre-processing activities as well as post-processing activities. And therefore, we have a multitude of capabilities in the entire area of SPF that we can then use to benefit our customers. So some examples of this, we've done a lot of work in new product development for SPF. So this perhaps would involve looking at a component which was previously manufactured from a different manufacturing method, analysing how suitable it would be for SPF, developing process cycles, and then carrying out tests on our manufacturing equipment to then understand how SPF could benefit and develop that component. Or perhaps looking at a new line of components within a family. So looking at perhaps increasing size of a component, understanding how that was then influenced by the SPF process, and then understanding how that would work for our customers. Data analysis and process cycle optimization is a really key area for us. And I'm going to give an example a bit further on in the presentation of a case study on that. So looking at perhaps a SPF component that had been manufactured already existing using SPF, and looking at the process cycles and how we can perhaps optimize that process cycle. As Paul mentioned earlier on in the presentation, one of the challenges of SPF is the length of time that it takes to actually form a component, and this can be multiple hours. So if we can optimize existing process cycles to try and reduce that overall cycle time, it can provide a huge benefit for customers by increasing throughput in quite an offline manner, essentially by using things like finite element analysis to do this. We have a lot of experience in tool design and development of structural analysis for tool design. So we look specifically at tools for SPF. As Paul also mentioned, these are quite a significant cost in a process. So it's very important that your tools are designed and optimized specifically for the components you're looking at. And this tends to be an iterative process between the finite element capabilities and then the design of the actual tool itself, as well as actually going through the structural analysis of the tool. We have advanced finite element and microstructural modeling capabilities, which I'll not talk about too much on this slide because we have a bit more in the presentation on that. But it really is a key aspect of our SPS process, and one of the really key capabilities we have in the team, from that mechanical testing that feeds into the modeling activity, and then we can use that to develop process cycles and understand the limits of a material before taking it and using expensive material on some of the presses that we have. We have experience in developing supporting technology and equipment. So we develop things like handling systems, things like the lubricants and coatings that I've spoken about and how they will interact with the process. So it's really looking at the pre and post processing. So alpha case removal, things like cutting technologies and what can be used as well to support the SPF process. A key activity they undertake quite regularly, not only for superplastic forming, but for a multitude of manufacturing processes within the AFRC, is a method of manufacture assessment. So a customer may come to us with an existing component or a new component, and we'll be able to undertake an assessment on that to understand how applicable superplastic forming will be. And that can be quite a light touch process if we want a fairly quick assessment, or we can go into quite significant detail with computer-aided design and finite element modeling capabilities to really understand the ins and outs of how SPF may benefit a customer for that specific component. As I've already mentioned, we have advanced material mechanical testing facilities for a multitude of different testing, and that can then feed into understanding the materials and feed into the FE modeling capabilities. And we have the capability to develop process cycles for novel materials as well. So things like perhaps materials that have been brought in from likes of Time-It or other material manufacturers, who then want us to understand how the material will behave in an SPF type environment. As I've spoken about, we have full-scale manufacturing equipment, which is quite a unique capability for a research centre and one of the real benefits we provide to our customers. And we also have the capabilities of pre and post processing development and analysis. So once you have formed your component, we want to make sure that we can then assess that component correctly to ensure that then we can understand how SPF has perhaps worked for that specific component. We typically do this through things like BOM analysis. So the component will be 3D scanned. Perhaps cross sections will be taken of that component and cut up so we can 3D scan inner surfaces, specifically if we were looking at a multi-sheet component. And we can then do a comparative analysis against things like the finite element modelling, and then understand how accurate our predictive finite element modelling has been against our real world component, which is a really key capability. And then that feeds into the loop of developing your FE model, developing your process cycle, optimizing that, and then retesting, rerunning, reanalyzing, and then understanding how your capability is there. And if we can do that, we can then predict cycles more accurately in the future, and then reduce that overall lead time for a part to be brought from an idea to a superplastically formable component. So Steph, just like to go to the next slide. So one thing I've spoken a bit about in some detail is our modelling and simulation capabilities. We have, as I mentioned, the capability to characterize material and then analyze this using commercial software, which we have access to a number of commercial softwares, including Abacus and PalmStamp. We have a close liaison understanding of the testing outcomes to be able to apply them, and we have then a specific team involved with actually developing these finite element models based on the tensile test data, the manufacturing parameters and capabilities that both we have and our customers have, to truly understand the capabilities and develop a very accurate process cycle, or things like very accurate temperature range that we want to aim for, and specific strain rate that we want to aim for, to ensure that when we do move on to the machines, that we can hopefully have a part that is formed correctly in the first instance. We also look at microstructure analysis and trying to understand how the microstructure behaves during the process, and that will, our modelling capability will allow us to predict some of that microstructure. Okay, next slide, please, Steph. Just moving on from this a little bit more and just showing some examples of the processes that we've used, and this is looking at a multi-sheet component and a single sheet component, so showing what our modelling may predict. And we've got a video there showing, I think it's a 4-sheet component to show the kind of honeycomb structure that we may be able to achieve within an SPF component, and how we use the modelling to predict that. And the graph there also shows how we can achieve both the pressure curve and the required tonnage that the press will need to utilise to then allow us to form that component. And really, as I said, it's an iterative process. We need to make sure that we develop the FE model based on the material characterization, based on the machine parameters, and then transfer that to the press, form real life components, and then bring that back after analysis and understand what developments and improvements that can be made to optimize that cycle. Okay, Steph, if you'd like to move on. Thank you. So now that I've talked about the capabilities that AFRC have, I want to give some specific examples of case studies. So we've got 3 case studies that I'll talk about in a bit of detail, and before we move on to our Q&A session. So a case study that we have, and this is a bit of an older case study from when we first started looking into SPF, and we wanted to understand how we could perhaps look at reverse engineering a component in order to understand and drive a specific forming cycle and pressure curve from that. So we had a tool, a die set that's shown there in the image, donated from a Tier 2 member. We looked at preparing the component, 3D scanning that part, digitizing the 3D scan, so understanding the specific meshes, and then developing that mesh to create a solid model. That solid model was then taken through an FE analysis with a sheet material, which has then allowed us to develop a forming cycle, which gives us our pressure curves and our tonnage requirements for the SPF process. And it's just an example of how we can even look at perhaps historic components which we don't have digital data for, and how we can develop those into usable information for superplastic forming. I'd like to move on to the next slide, please, Steph. So one of the significant case studies that I'd like to talk about is an example from a Rolls-Royce program that we completed a couple of years ago now. So as Paul mentioned, Rolls-Royce develop and manufacture fan blades along with the entire engine. And the fan blades are historically superplastically formed using a warring girder structure on the inside and with multiple sheets of material. Rolls-Royce have been making fan blades in this manner for 30, 40 years, and they came to us to understand if we could try and optimize their process cycle in order to increase the volumes that they were able to produce, rather than having to invest in machinery to try and increase that throughput. What we did as the centre was we carried out an extensive data mining activity on many, many years of Rolls-Royce manufacturing data, and we were implemented quite specifically within the Rolls-Royce facility. So we would spend a significant amount of time with the engineers at the Rolls-Royce facilities, the technicians who use the press, to try and understand where there are challenges in the process, to try and understand where we might be able to overcome some of these challenges and optimize that process cycle. And it wasn't just on the specific process cycle of the SPF part, it was on some of the pre and post processes and complementary activities that we've spoken about as well. We took that data, we understood that data, and it allowed us to analyse varying sections of the SPF cycle, so doing things like interrupted tests and cycles to try and then understand our manufacturing capabilities on real life components, to try and understand what stages of the cycle we could perhaps optimise further. We developed novel temperature measurement instruments to try and understand how we could more accurately monitor the cycle, which is a very difficult thing to do because you have a press running at 900, 950 degrees, and in-house monitoring with measurement sensors and so on is very difficult in that kind of environment. And through this, we undertook full-scale fan blade trials on our 1,200-ton press to try and optimise that process cycle and the complementary aspects of that process. So the business impact that then had for Rolls-Royce was quite significant. As a direct result of that, we were able to develop and optimise the SPF inflation curve with an overall 27% reduction in cycle time. As Paul mentioned, these processes can be multiple hours long, so that really is a significant saving when you have multiple presses running at one time. And if you can reduce our cycle time by 27%, you can potentially then increase your throughput by this amount. This is then validated on production trials within the Rolls-Royce Barnoldswick facility, and then coupled with other studies on dial-life extension, it allowed an increase in SPF capacity that helped to mitigate the original plans and the costs then associated with putting in new machines for SPF. We've got a quote here as well from Stephen Halliday, who's on the call today, and thanks Stephen for joining us. And Stephen's been a real key part of the AFRC and the relationship we have with Rolls-Royce and the development of SPF that we've done over the past few years. The quote he's left us here is that the strong collaboration between the AFRC and Rolls-Royce engineers was needed on this project, and I mentioned that we really implemented ourselves throughout the facility at Rolls-Royce, and we worked together as part of an integrated team, influencing a critical manufacturing process that had historically seen little change, and allowed the SPF rigs to be implemented to achieve the data necessary for validation of the cycle time reduction in that production environment. So a really successful project example for us, and something that was a really interesting program to work on over multiple years to really embed ourselves within this manufacturing process, which has then led on to multiple projects throughout the years also. So Steph, would you like to move on to the next slide? So another example again with Rolls-Royce. This was one of the examples of a complementary process. So I mentioned a bit about coatings and lubricants that are used for the SPF process. Specifically, the lubricant boron nitride tends to be sprayed as an applicator to a component prior to the manufacturing process. And this allows to be both an oxygen inhibitor and also prevent from sticking to the die essentially during the process. So allows a bit of lubrication to more easily remove components at the end of the process. Now, this is typically sprayed manually onto parts, but that variation can lead to different, like that thickness coating variation from a manual spray can lead to perhaps issues. Things like sticking to the part if too much is sprayed, or alpha case, and oxidization if there is not enough coating on the component. So we are trying to understand how we could minimize that variation of spray application through an automated method. So we worked in collaboration with Rolls-Royce to develop and demonstrate an automated method for application of boron nitride to Trent 700 fan blades. We installed an automated spray system at the AFRC with use of robotics, and we demonstrated trials through spray coating fan blades, and these were then formed in our 1200-ton press, as well as analysis being done on coating thickness and the consistency that we were able to achieve for that. So the business impact result of the investigation and the demonstration helped to reaffirm the business case to install similar spray coating systems within Rolls-Royce manufacturing facilities, which has now been undertaken, and they are installed within Rolls-Royce facilities. And the industrialization of that automated spray system was expected to bring further benefits in die life, so trying to increase die runs of a component to ensure that you could have less downtime of your machine to clean dies and to change over dies during recuts, and as well for post-processing and reducing potential waste in the process. Another quote here from Stephen, just stating that the AFRC's knowledge and expertise from previous SPS-related projects for Rolls-Royce was key in allowing us to understand the best approach to developing the automated boron nitride application. And I think a lot of what we've learned in the past has allowed us to really build upon this and develop our capabilities further, and then really help our customers in that manner. If you'd like to move on to the next slide. We won't dwell on this for much. It's just a list of our forming team publications and some examples of the work that we've done that have been undertaken either by the FRC independently or as part of our core research programme, or in collaboration with a customer through a directly funded project or a collaborative research and development programme. So as we mentioned, this webinar will be put online, so I think in the future, if you'd like to have a look at this list and refer to any of these publications, then please do. If you'd like to move to the next slide. So that's everything from myself. Just like to thank you everyone for listening. I understand it was probably a lot of information to go through in a fairly short space of time. So at this time, we would really like to welcome any questions from everyone here. Thank you.
Thanks very much, John. Thanks very much, Paul. And thank you very much for everybody getting the questions in on the chat. So we've got a couple for you guys. I'll just bring up these here. So Florian from TGM has asked, what are the typical limits concerning the dimensions of the part manufactured?
I suppose go on, Johnny, do you want to pick that up?
Oh, well, why don't we'll go together, Paul? You start and I'll add if needed.
Okay, well, I suppose in terms of dimensions, it depends on the press. Obviously, the larger the size of the part, the bigger the press you need to balance against the gas pressure required. Our own press, as we've told you, is about 2 meters. There are bigger ones around, certainly. In terms of the sort of tolerances you can hold, well, as I mentioned earlier on, SPF is a net shape forming process pretty much. It depends on the tolerances of your tooling. With the titanium part, you would normally, as I mentioned, in my preamble, you would normally need to take the part and remove some alpha case off it, so you need to allow for that. With aluminium, no issues there really. Aluminium doesn't really suffer from the same problem. So in terms of the accuracy of the process, pretty tight. I mean, obviously you've got to be able to get the part out of the press. So you'll need a certain amount of radius on the sort of sharp edges, but other than that, a fairly accurate forming process, and that's really one of its big selling points. I mean, the fact that the material superplastic means that you can form the sort of fine detail that that is one of the big sort of value adds of this type of process.
Absolutely. John, do you want to add anything to that?
No, I think Paul's covered that sufficiently.
Excellent. Another question which was asked but answered in the same vein from Peter, just regarding how well is the relationship between temperature and pressure rate understood, but I think we answered that in the presentation. But Peter, was there anything else that you wanted to add to that, or any other clarifications that you need? You can unmute yourself. Okay, he says no, thank you, no problems. Okay, from Adrian Nicklin has asked, does thinning happen on the component radii?
The answer is yes, of course it does, and it just depends on the radii, which is kind of what I was pointing out a little bit in the answer to the last question. We do get some thinning, but the nature of superplasticity is that as thinning starts to occur, the local strain rate will go up, and the material actually gets stronger. So one of the properties of superplastic materials is that they're very sensitive to strain rate, and that's actually one of the main things that makes them superplastic. So yes, we do get thinning, and that's why we spend a lot of time actually modeling the process to try and ensure that that thinning is not unacceptable to the manufacturer. But yeah, thinning obviously is unavoidable in any sort of drawing type process, but probably much rather less than you might see in a sort of conventional cold deep drawing process.
Thanks very much, Paul. John, anything to add?
No, that's fine.
Okay. And apologies if I'm not pronouncing your name here. We have got your Dare, who has asked, in FE modelling, has, I'm assuming COF is coefficient of friction, considered constant or variable?
It'd be useful to talk to Diego on this. I mean, we did some experiments quite a few years ago to measure the coefficient of friction using a ring test for boron nitride, and as I recall, and it's been a while since we did this, it was about 0.2. So as far as I'm aware, we would tend to assume a constant coefficient of friction for the sort of modelling that we do. Obviously, in truth, the coefficient of friction will vary a bit as the thickness of the boron nitride itself varies as the material actually gets drawn across the tool surface. But that's actually quite difficult to measure, as you'll appreciate. So to all intents and purposes, unless one of the modelers from the AFRC is on the call, we would tend, as far as I'm aware, to assume a constant coefficient of friction of that kind of number.
Okay. A follow-on from your Dare as well. Has FE modelling been done? Oh, sorry, I'll read the full thing here. I can see from images of flow stresses that have shown softening behaviour after certain strain values. My question is, have FE modelling been done with these softening behaviours or assumed to be very slightly increased? What is the accuracy level of FE compared to experiments? Yeah,
well, we've done a lot on this over the years, and yes, we certainly can model flow softening. One of the slides that John flashed in front of your eyes, there was a set of equations which were fairly standard equations that are used for FE for sort of material constitutive models. So they're fairly easy to match up in actual fact. We use the step tests, by the way, to actually give us an instantaneous measure of the rate sensitivity, which can change obviously as a function of strain. So you've not only got the flow stress dropping in the case of that particular alloy, but also the rate sensitivity itself can change, and that's something that you want to know about because you need to factor that into your constitutive model. So to answer your question is, can we actually represent that into a set of constitutive equations? Yes, that's relatively easy to do. And that particular alloy did flow soften. Other alloys actually flow harden slightly due to grain growth, and we can pick up either that. It's obviously due to what's going on in the microstructure. If the microstructure is refining during deformation, it tends to flow soften. If we're getting a bit of grain growth, which is typical in many cases, it would tend to flow harden slightly. And we can pick up either that in a constitutive equation without it all becoming too complicated.
Thank you very much. Hopefully you'll be pleased to know this is the part one of a series from the AFRC's forming team. Part two will be a webinar on modelling itself. So hopefully if you can come along to that one, we'll be able to dive in a little bit more into the capabilities and obviously the benefits of using finite element modelling. There are some typical questions that we get in terms of SPF, especially myself when I'm out and about. And I think John, you pretty much kind of answered them in some of the case study examples. But there are some people who just generally ask, how, in what ways or what capabilities does the AFRC have that would help our customers make the process cheaper? And I think we've probably covered that in the majority of the slides in terms of understanding the end-to-end processes. which we have a very capable understanding of all the ins and outs of from the start to the end. So I think usually a full review of the extent of the customer's processes does help that. But is there anything else, John, that you've maybe experienced, obviously without breaching any IP laws, that you've experienced that we've been able to do that we've maybe not picked up on today, that's helped somebody perhaps look at the SPF process, make it a bit cheaper?
I think, as you say, it's really about understanding the end-to-end process, and a lot as well about putting in the upfront work to understand the process before you actually go to manufacturing trials. And that's where we can see the key benefits from Superplastic Forming and the modelling capabilities that are held within that area. Fortunately, it is a process that has high modelling capabilities, and we can use those to predict that process. Titanium stock tends to be very expensive. So if you were using multiple sheets to try and understand your forming cycle rather than doing this as an iterative operation on a computer-based modelling system, that would significantly increase the cost of development of that process. So having that upfront work activity done, which is one of our key capabilities, is really essential. And as well as that, we've also spoke about today how you can have perhaps understand an assembly of components and how you can reduce the overall number of components in an assembly. With use of superplastic forming and the more complex geometries that it perhaps is able to manufacture. So it's really a combination of these aspects and running that assessment and review of the whole process for a customer, which you could potentially then see the benefits of cost reduction.
Thank you very much. Okay, if there are no further questions, we thank you all for participating today. Hopefully you found it useful. And that you'll stay tuned for the series from the AFRC's forming team. And if there are any questions, there are email addresses on the slide there. Please feel free to contact me for any information directly related to the AFRC's forming team. And please send any general inquiries to the NMIS inquiries email address that you see on your screen.
Right, thank you.
Thanks, everyone.
Thanks, everybody.
Thank you very much.
Thank you.
Thank you, everyone. I'm just going to stop the recording and end the session here. Okay. Thanks very much.
Thank you.